Greetings! Isang pagbati na puno ng kaalaman. Our lecture for today is a continuation of the double integration method. Last meeting, we were able to solve for slopes and displacements at arbitrary points in the beam. However, what is much more important is that we should be able to locate the maximum deflection and determine its magnitude. Why? Because in analysis problems of transverse members, given a certain amount of loading, we would be able to determine how much deformation is experienced by the beam. And yung kabaliktaran naman, the opposite, in design problems, given an allowable deflection, we would be able to determine the maximum load that can be applied in the member. This is lecture number 18. Now, our first task when we are determining the maximum deflection is to find its location. So there are several plausible locations for us to be able to find the maximum deflection. Number one is at points at which the slope of the tangent line to the deflection curve is equal to 0. Now take note that the deflection curve is also known as the elastic curve. Okay? So where do we normally see points at which the slope of the tangent line to the elastic curve is 0? Look at the figure over here. Okay? This is a good example of where we normally see tangent lines, right, whose slopes would be equal to 0. If you have a member which is simply supported, meaning you have a pin and a roller, somewhere between these 2 points, there is a location wherein the slope of the tangent line is equal to 0. The second plausible location is a free end. Where do we normally see a free end? If we have a cantilevered beam, meaning fixed at one end and free at the other, or a simply supported beam with an overhang. And the third plausible location are called internal hinges. In ES 102, we will be concentrating on the first two plausible locations. Now, trying to look at the first plausible location, how do we determine where the slope of the tangent line to the deflection curve is equal to 0? Now, if the slope of the tangent line to the elastic curve is equal to 0, we should know that since the slope or the tangent line is horizontal, dy over dx is 0. Therefore, since we know the value of dy over dx, which is equal to 0, our task is to locate where that occurs, is to locate where, at which point in the entire length of the beam does dy over dx become equal to 0. Once we can now locate the distance x, where dy over dx is equal to 0, we can simply substitute the values and solve for the maximum deflection. Any questions? So at this point, let's already try to look at an example. Determine the maximum deflection of the simply supported beam with a modulus of elasticity of 200 gigapascals and a moment of inertia of 65 times 10 raised to 6 millimeters to the fourth. And where does it occur? So I have here, if I look at the figure, this is a simply supported beam. Therefore, our first task always is to locate where does it occur. And a plausible location is, of course, we don't have any free end over here. We don't have an internal hinge. Therefore, the only plausible location is somewhere between points A and B, where the slope of the elastic curve is equal to 0. So at this point, I'd like you to look at the example, grab a copy of the example while I set up and solve the problem. Now, So this is example number 18.1. I hope you already have a copy of the problem. Now, our first task, okay, step 0, as you may notice in the screen, okay, the summary of the steps are actually similar to our past lesson. So step 0 is use equilibrium in order for us to solve the support reaction. So at home, kindly show that the support reactions would be AY is equal to 25 kilonewtons upward, and BY is equivalent to 20 kilonewtons upward. Okay? Next, step 1 is to establish the coordinate system. So for us to not have any difficulty in solving the problem, let's use the conventional coordinate system. I'll use the origin at the leftmost end, which is at A. Okay, so that's my x is equal to 0. Then my positive direction is to the right. Okay, now again, as a review, if my positive direction is to the right, what is considered as the end of the beam? Okay, so when we say end, we are referring to, if positive is to the right, yes, that's correct. The end is B. Okay. Next step, we now write the moment function. And again, it's stated here that the force reaction By is not included since it's found at the end of the beam. Okay? Therefore, let's now write the moment function. Our moment function will be d squared y over dx squared is equal to 1 over EI times the support reaction at A, that's upward. So that's 25 kilonewtons, x minus 0. So x minus A, because A is equal to 0, because the 25 kilonewton force is found at the origin, raised to 1, minus 30 times x minus 2, because the load is found at x equals 2, and negative 30 because the load is downward. Similarly, the 15 kilonewton downward force, that's negative, times x minus A, but A is equal to 4, raised to 1. Okay, so this is now my moment function. Okay, next step is to perform double integration. So to perform my double integration on the moment function, I integrate once. I should be able to get this equation. Kindly double check if my answers, if my solution is correct. Don't forget the constant of integration, C1. Then I integrate again this equation. This is my second integration. I now get y, which is the equation of my elastic curve. So this is now the deflection curve or the elastic curve. Do not forget that once I integrate, I now have again C1x and another constant of integration C2. The next step, step number 4, is to apply the boundary conditions in order for me to solve for the constants of integration. Now again, please take note that if the value inside the bracket is negative, the value becomes 0 and there's no need to evaluate that term. Now, again, just as a review, when we say boundary conditions, our target points are actually the support reactions. Now, I have two support reactions, a pin and a roller. So what are the boundary conditions involved if we have a pin and a roller? The deflections at the pin and the roller are both equal to 0. That's correct. Therefore, our first boundary condition is just y equals 0 at x equal to 0. Therefore, using my equation B over here, I can say that y is equal to 0 equals 1 over EI. I'll just copy equation B over here, but what I'll do is I'll substitute the value of 0 to x. So let's just copy that. That's 12.5 over 3. times 0 minus 0, cube, minus 15 over 3, that's 5. 0 minus 2, cube. 7.5 over 3, that's 2.5. 0 minus 4, I'm just substituting x equals 0, cube, plus C1 times x, that's 0, plus C2, okay? So let's now try to look at the entire term, the entire equation. That's 0. 0 minus 2, negative, so that's 0. 0 minus 4, that's negative, so that's 0. C1 times 0, that's 0. Therefore, C2 is actually equal to 0. Okay? Next, let's look at the next boundary condition. We mentioned that at the roller, okay, y is equal to 0 at another support reaction, which is found at x is equal to 6. So using the same equation B, I can say that y is equal to 0 is equal to 1 over EI times, again, I'll just copy equation B, but I'll substitute a value of 6 to the variable x. Okay? So that's just 12.5 over 3 times 6 minus 0 raised to 3 minus 5, 6 minus 2 cube minus 2.5, 6 minus 4 cube plus C1 times 6 plus we have already solved that C2 is equal to 0. Okay? Therefore, if we look at all the terms, well, no term inside the bracket becomes negative. Therefore, I need to evaluate, okay, such that you can solve that C1, okay, is actually equal to negative 280 all over 3. Okay? Now that we have solved for the boundary conditions, I can already solve the problem. To find the maximum deflection, always, okay, once you have finished solving the boundary conditions, the next step always is to locate. Before even determining what the maximum deflection is, you first need to find out where, okay? You need to find out where the maximum deflection is, okay? So that's always the initial step. Where is the maximum deflection found? It can either be, we mentioned earlier, between supports where dy over dx is 0 and at the free end. However, in our problem, we actually do not have a free end. Okay? Therefore, I will just cancel this second one. There's no need, okay, to check this one because there's no free end. Okay? So we only check between the supports, okay, and find where dy over dx is equal to 0. Okay? Now, if we look at the problem, kindly go back to the problem. I need to pick a guess location where dy over dx is equal to 0. And based on the loading conditions, there are actually 3 possible locations. I can either say that dy over dx can be 0 between 0 and 2 meters. It can be between 2 and 4 meters. And it can be between 4 and 6 meters. So this is due to the difference in loading per span of that beam. Now, what I do is, I just need to guess first or make an intelligent guess as to which location dy over dx is found. Okay? So I can select 1 out of the 3. So for this example, let's say that I will guess that using my engineering intuition, I'll say that it's found between 2 and 4. Okay? So I'll say that x, the location of the max deflection, is somewhere between 2 and 4. So the value of x is larger than 2 and smaller than 4. It's between 2 and 4. Okay, therefore, if we look at equation A, yes, I will go to equation A. Why equation A? Okay, I'll use equation A primarily because I am looking for where dy over dx is equal to 0. Therefore, I can say that, okay, from equation A, this is equation A, okay, I will just equate dy over dx to 0, and I'll solve for x, okay, where that happens. However, please be careful. Why? Please remember that I assumed that dy over dx, the location of where dy over dx is 0, is between 2 and 4. We always need to make this assumption. Why is it important? Because if the value of x is somewhere between 2 and 4, okay, and we look at these three terms over here, if my value is larger, is between 2 and 4, will the value inside this bracket be equal or be negative? Any value of x between 2 and 4? It won't. Right? How about this second term? Any value of x between, we mentioned 2 and 4. Will this bracket, will the value inside the bracket be equal to 0? Be negative, rather. It won't. Okay? So we evaluate. However, right, what if we look at this third term and say we assumed again that x is between 2 and 4? Okay? Take any value between 2 and 4. Will the value inside the bracket be negative? Yes. Therefore, what does that mean? We cancel this term. Right? Because, again, whatever happens if we assume that x is between 2 and 4, okay, any number between 2 and 4, the term, the value inside the bracket will be negative. Okay? So do not forget that step. Okay? So the third term will be equal to 0. Hence, our updated equation, if we assume that x is between 2 and 4, is just dy over dx equals 0. Okay? 1 over ei. Okay? Let's just copy that equation A, 12.5 times x minus 0 squared minus 15 x minus 2 squared minus 280 over 3, okay, which is C1. Well, I already canceled the third term because, again, any value of x between 2 and 4 will yield, okay, a negative number inside this bracket. Okay? Now, going back to this equation over here, okay, I can now solve for the value of x and try to solve the value of x. I'll wait for you. Get your calculators. Okay? You should get a value of x that is equal to 2.9079 meters. Now, 2.9079 is indeed, okay, less than 4 meters and greater than 2 meters as we have initially assumed. Since our answer is correct, okay, since our answer is within our initial guess, therefore, our assumption is correct that indeed maximum deflection occurs between 2 meters and 4 meters. Okay, let's pause before we continue. Sir, what if I didn't assume that the max deflection will occur between 2 and 4? Say, what if, sir, I assume that it's between 0 and 2. Okay? If we assume that it's between 0 and 2, what happens? Okay? If we assume that it's between 0 and 2, actually, okay, this first term, any value between 0 and 2, will it be positive or negative? It's positive. So we evaluate. How about the second term between 0 and 2? That's negative. So it cancels out. How about the third term between 0 and 2? Okay? Any value of x between 0 and 2, if I evaluate that term, it's negative. So that cancels out. Then, if I solve for x, given that the only terms left would be the first term and C1 over here, solve for x, and you should get a value of x that is not within 0 and 2 that you assumed. Are we clear? Okay? So meaning you always go back and look at the value of x that you obtained if it is within the range that you have initially assumed. Okay? Therefore, we can say, since our answer is within the range of our initial guess location, our initial assumption is correct. Therefore, y max occurs at x equals 2.9079 meters to the right of point A. Okay, now that we know the location, we can now immediately solve using equation B. Okay? So using equation B, okay, I can now solve, so this is equation B. Okay? I can now solve for the deflection. Okay? Therefore, I can now, so I'll just copy equation B. Okay? So from equation B, I can say that y max, I can now solve for the maximum deflection at x is equal to 2.9079. So I'll just copy equation B, but plug in the value of 2.9079 as x. Okay? So that will give me 1 over EI times, I'll just copy equation B, that's 12.5 over 3 times x minus 0, but I'll use x as 9079 minus 0 cube minus 5 times, I'm just copying equation B, okay, but substituting or using the value of 2.9079 as x, okay, minus C1x, okay, C1 is 280 over 3 times 2.9079, okay? So C2 is equal to 0, so I won't include it in the equation. Okay, therefore, if we look at this, kindly take note that this term over here becomes 0 because the value inside the bracket is negative. Okay? So once I evaluate, I can say that, kindly confirm, this is negative 172.6922 kilonewton force, unit, force, length, cube, if that's deflection, okay, all over EI. Okay? So since I'm very familiar with newtons and millimeters, I can say that this is negative 172.6922. Then I multiply it by 1,000 raised to 4 for this to be equal to Newton millimeters to the fourth, all over EI, 200,000 megapascals times I is 65 times 10 to the 6 millimeters to the fourth. I should get an answer of negative 13.28 millimeters. Kindly double check and kindly confirm. Okay? And final answer, that becomes 13.28 millimeters downward. Okay? Are there any questions? Okay. So that is example 18.1. Okay? That is how to determine the how to determine the maximum deflection once we are given a simply supported beam, or how to locate the maximum deflection where dy over dx is equal to 0. So that is example 18.1. Okay. Now, how about example 18.2 over here? Let's try to look at the next example. Okay. Determine the maximum deflection of the cantilevered beam given a modulus of elasticity of 200 gigapascals and a moment of inertia of 65 times 10 raised to 6 millimeters to the fourth. And we're being asked, where does it occur? Okay. So again, at this point in time, kindly get a snapshot, get a copy of this example before I transfer, right, to my solution. Okay, before I transfer to my solving screen. Okay? Now, if we analyze this example, right, don't worry, right, because the initial steps are still the same. Right? First, I need to use equilibrium in order to solve for the support reactions. Kindly show at home that the support reactions, we have a fixed support, right? So you have a force reaction, AY, which is 37.5, right? Oops, that's 3, right? 37.5 kilonewtons upward. And the moment reaction at A is equivalent to 67.5 kilonewton meters, and that's counterclockwise. The next step is for me to establish the coordinate system. Okay? So the coordinate system, first, I need to establish two. The first one is to establish the origin where x equals 0. I'll use our conventional, the easiest one, the leftmost portion. I'll use A as x equals 0. Okay? So I have a figure here. So it's here at x, that is x equals 0. And my positive direction is to the right. Okay? And therefore, if to the right, what is the end of the beam? If positive is to the right, the end of the beam is the rightmost end. Okay? End is the free end. Okay? This one, or where, okay, my 15 kilonewton load is found. Okay? The next step is to write the moment function. Okay? So again, since my end is the rightmost part, okay, remember that the 15 kilonewton force is not included since it's found at the end. I have here a triangular distributed load, but go back to our copy from last and our lesson from the previous lecture. For our moment functions to be valid, right, the distributed loads should be loaded up to the end. And as you can see in the figure, it's actually not loaded up to the end of the beam. Therefore, I need to perform what we call the dagdag-bawas method. Okay? So again, my goal is to come up with a distributed load that looks like, okay, what we have shown in the previous lectures. Okay? So in this case, what I'll do is I can just extend. Okay? So I'll have here a triangle. Okay. Correct. Okay. So that now looks like what we have shown in the loading in our previous lecture. I have a triangle that is loaded up to the end. Okay. However, whatever I added, I also need to remove. So kung anong idinagdag, siya ring ibabawas. Okay, having the same magnitude but opposite direction. So I actually added a trapezoidal load, okay, such as this one. Now my question is, what's the value? Okay, what's the intensity of that triangular load? So let me call that y. Of course, if that's y, this is also y. Right? So what I can do is, anyone? Okay, what's my next step? I can actually perform similar triangles. So using bisimilar triangles, okay? So bisimilar triangles, what I can do is, I can say that I have 30 over 1.5, so 30 all over 1.5, okay? Can you see the similar triangles? Is equal to y, this one, the larger triangle, all over this entire length, which is 3. Therefore, y is equal to 60, right, kilonewtons per meter. Okay? So this is equivalent to 60. Okay? Same with this one. Okay? Therefore, I can now write my moment function. Okay? And again, I'll just copy. I know that I have an upward load, 37 force, 37.5 kilonewtons, and a counterclockwise moment, which is 67.5 kilonewton meters. Okay? So I can now write my moment function. Okay? So d squared y over dx squared is equivalent to 1 over ei times, okay? I'll start with the force reaction. That's 37.5 x minus 0 because it's located at the origin, okay? Raised to, if that's a force reaction, raised to 1, okay? Next, how about the moment reaction? I have a counterclockwise moment reaction. So going back to our previous lecture, that counterclockwise moment reaction will be negative 67.5 x minus 0 raised to 0. Okay? Next, how about the triangular load that is downward? So going back to our lecture again from last week, from last meeting, okay? It should be m over 6, where m is the slope. Okay? So again, the magnitude, this is negative because it's downward. M over 6, m is the slope. Okay? So meaning it's just 60, okay? This value all over the width. So to get the slope, it's rise. Okay? This height divided by the width over here. So it's 60 all over 3. So that is the slope, m all over 6. Okay? So times 6 over here. X minus 0 because it started at x equals 0 raised to, that's a triangular load, so raised to 3. Next, how about this one? Okay? How about this portion over here? Okay. So that portion, okay, that portion is actually a trapezoid, you might say. Sir, we didn't discuss any load that is trapezoid. However, that trapezoid can actually be subdivided into two. That trapezoid can actually be subdivided into, that trapezoid can be subdivided into a rectangle and a triangle. Right? Correct. Okay, and look at that trapezoid. That trapezoid actually still obeys our rule from last lecture that, right? From our last lecture that the distributed load should be loaded up to the end. Look at this rectangular portion. It's loaded up to the end. How about this triangular portion? It's still loaded up to the end. Okay? So if you forgot that lecture, okay, you may revisit our previous lecture. It's already uploaded as well. Okay? You may visit the other videos uploaded, the other video uploaded for a review of your double integration method. Okay? So first, I look at the rectangular distributed load. That's upward. So I have positive. Okay? So positive, I'll first look at the what do you call this one? Rectangular distributed load. Okay? That rectangular load is, of course, this is actually 30. Right? So if this entire thing is 30, going back, right, the smallest magnitude that we added is 30. So this is 30. And this here is 30 as well. Okay? So that I should have, okay, 30 all over 2. Okay? Going back, if I have a uniformly distributed load, it's omega over 2. So 30 all over 2. X minus a, where did it start? It started at x equals 1.5, okay? Raised to 2, because that's a uniformly distributed load, plus, okay, the triangular portion of the trapezoid. Okay? Remember, I'm not using 60, okay, because 60 is the entire trapezoid. So what is left only is this portion, which is 30 kilonewtons per meter. So again, right, to get the magnitude of, in the moment function of a triangular distributed load, it's m over 6. So slope all over 6. So the slope is just 30, the intensity omega, all over the width, right? So 30 all over the width, which is 1.5. So that's the slope, right? M over 6. So don't forget, it's m over 6. X minus 1.5 because it started at 1.5. That's a triangular distributed load raised to 3. Okay? So this is now my moment function. Hey, Next, I now perform double integration in my moment function. I integrate twice. Okay, so this is my first constant of integration. Okay, then I integrate second time again, okay, to get the equation of my elastic curve. Lastly, okay, I'm going to apply my boundary conditions to solve for C1 and C2. Note that again, if the value inside the bracket is negative, the value of that term becomes 0. Right? So I have a fixed support. Right? I have a fixed support. Therefore, right, what are my boundary conditions? Okay? So again, my boundary conditions would be, since that's a fixed support, I can say that dy over dx is equal to 0. The slope is equal to 0. That's only valid if we have a fixed support as a boundary condition at x equal to 0. Okay? So I will be using equation A, okay? But substituting x equals 0, or substituting 0 as the value of x. So I'll just copy, let's just copy equation A. Okay? So altogether now, I can say that's just 0 is equal to 1 over EI times, I just copy everything, okay? 37.5 over 2. I'll substitute 0 as the value of x, minus 67.5, 0 minus 0 raised to 1, minus 10 over 3 all over 4, 0 minus 0 to the fourth, plus 15 over 3, okay? 15 over 3, 0 minus 1.5 raised to 3, plus 10 thirds all over 4, 0 minus 1.5 raised to 4, plus C1. Okay? And if we evaluate, that becomes 0, 0, 0, 0 minus 1.5, that's negative, so that's 0. 0 minus 1.5, that's negative, so it's 0. Therefore, C1 is actually equal to 0. Okay? Next, boundary condition. My next boundary condition is that y is equal to 0. Again, at the fixed support, the deflection is also equal to 0. Okay? So what I'll do is, I'll just use equation B over here and equate that to 0. But I will use the value 0, okay, for the variable x. Okay? Therefore, that's just 0. Okay? Oops, that's just 0 is equal to 1 over EI. Okay? Times, I'll just copy everything from equation B over here, but substitute 0 to x. That's 18.75 over 3. 0 minus 0 cubed minus 67.5 all over 2. 0 minus 0 squared minus 1 over 6. 0 minus 0 raised to 5 plus 5/4. 0 minus 1.5 raised to 4 plus 1 over 6. 0 minus 1.5 raised to 5 plus C1x. But C1 is already 0, so I'll just write 0 over there plus C2. Okay? If we look at this, 0 minus 0, that cancels out. 0 minus 0, 0 minus 0. 0 minus 1.5 is a negative value. That's 0. 0 minus 1.5 is still a negative value, so that's 0. Therefore, C2 is also equal to 0. Okay? Next, we can now solve the problem. And we mentioned that to find the maximum deflection, okay, our plausible locations would be either between the supports where dy over dx is 0 and at the free end. However, okay, we have a cantilevered beam. We don't have two supports. Okay? So we can already cancel this first one. But sir, dy over dx, I know where dy over dx is in that example. It's at the fixed support. But of course, that's wrong, or that's not a location of a maximum deflection because it's actually a boundary condition. It's a support reaction wherein dy over dx is 0. But then again, the deflection is still equal to 0. Okay? So it's not a location. The fixed support is not a location. Therefore, it is actually at the free end. We already know the location of the free end. Y max occurs at the free end or at x equal to 3. Therefore, going back, I can now use equation A. So I will be solving Y max, or the maximum deflection. Again, when we say maximum deflection, we're only dealing with the magnitude. So the maximum deflection at x is equal to 3, or the free end. So I'll just use equation A, copy equation A, but I'll substitute the value of 3 to x, to the variable x. So from equation, not equation A, it's equation B. Apologies. Equation B, where I am using the equation for deflection. So equation B, I'll just copy everything. That's 1 over EI, 18.75 all over 3. I'll just copy but substitute the value of 3 to x. 3 minus 0 cubed minus 67.5 all over 2. 3 minus 0 squared minus 1 over 6. 3 minus 0 raised to 5 plus 5 over 4. 3 minus 1.5 raised to 4 plus 1 over 6. 3 minus 1.5 raised to 5. C1 and C2, they're both equal to 0, so I don't need to write them anymore. So that cancels out. Now, if I look at all the terms, well, everything is positive inside the brackets. Therefore, I need to evaluate, and you can solve it at home. Kindly double check with your calculators that if I evaluate this equation, that gives me negative 5,373 over 32. I didn't convert anything, so force length cube, because it's deflection, all over EI. Therefore, to convert everything, that's negative 5,373 over 32 times 1,000 raised to 4 Newton millimeter cube all over 200,000 megapascals times 65 times 10 to the 6 millimeters to the 4th as I. Therefore, this will give me negative 12.92 millimeters, or 12.92 millimeters downward. This is now our final answer. Any questions so far? Any clarifications? So that is how to solve problems if we are dealing or trying to solve maximum deflections using the double integration method. Now, that ends our examples, our solved examples. At home, what you can do is try to solve the additional practice problems. So here in this example, I have a simply supported beam with a simply supported beam with an overhang. So there are, just as a hint, there are two possible locations. We mentioned that a possible location is between the supports where dy over dx is 0. So I'll solve somewhere, I'll locate between A and C, and that's an overhang. So I also have a free end. So I also need to check. So I need to check two locations between A and C where dy over dx is 0 and at the free end or at D. So check those two possible locations. So the larger deflection is your maximum deflection. And another practice problem over here. So that ends our lecture on maximum deflection for the double integration method. Again, please do remember that if you have problems with this lecture, try to go back to our previous lectures. I'll show the link somewhere, so that you can review the basics of the double integration method. I hope everything is clear. If you have questions, you know how to reach me. You can send me a PM or you can send me an email. And until our next lecture, I hope you learned a lot. This is Mechanics of Deformable Bodies.